Hello and welcome to 4K and Ultra HD, What You Need to Know. This should be an interesting hour presentation to give you some nuts and bolts about 4K Ultra HD, the terminology, the technology used to display it, where the content will come from, and all the other considerations that make this interesting ecosystem up. I'd like to thank BenQ for sponsoring today's presentation. And I will mention here, and again, there will be a survey available to all attendees. The link to that survey will appear in the chat box. If you'd be so kind after the presentation to take a brief moment and fill out the survey, we would greatly appreciate it. So without further ado, let's get started. I guess most of you know that 4K is everywhere on every device. Ultra HD cameras, both consumer and professional, and displays have been with us for quite a while. TV screens and monitors are getting bigger and cheaper. 4K content is becoming widely available, mostly from streaming and also from Ultra HD Blu-ray. Gamers, big chunk of the market, have moved to 4K resolution with ever faster laptops and computers. Smartphones and tablets can capture 4K video, not all models, but many of them can. You might be surprised to find out that your own phone can actually capture 4K video. The new broadcast standards being proposed around the world can support 4K programming. The display interfaces to connect all these things have had to get faster. They were slow for quite a while, and now there's been a kick to make them faster because, as we'll show a little bit later in the program, the amount of data going to the display from a content source has increased considerably. So again, that's the need for faster display interfaces. And more importantly, it's not just that we have 4K available, we also have some enhancements to it. We have high dynamic range associated with it. We have a wider color space, more shades of color that we can see. And also a really cool function, faster frame rates, higher frame rate video. These are all part of this transition from full HD to 4K. And of course, now we have 8K video arriving. I won't spend much time talking about that. That would warrant its own seminar, but that is lurking in the background. It's worth going back in time a little bit just to see how fast this all came about. The first 4K, or more accurately, Ultra HD TVs landed in the US in 2012, and they were quite expensive. They ranged anywhere from $18,000 to $25,000, and they were basically monitors with multiple HDMI inputs. But only a year later, at International CES, Ultra HD TVs were everywhere. Everybody was showing multiple models. The year after that, we started to see curved screen Ultra HD TVs at CES. And in 2015, you couldn't throw a rock without hitting a 4K TV someplace. In 2016, we started to see talk about high dynamic range, adding high dynamic range to these high resolution images. 2017, we saw the first 8K TVs at CES and the first 4K monitors. These are displays without audio, but for commercial applications and also for broadcast applications, show up at Integrated Systems Europe and Infocom. 2018, 8K TVs were everywhere at CES, just like 4K TVs were back in 2014. You saw a larger selection of 4K monitors and some LED walls that with 4K and 8K resolution at both ISE and Infocom. And at 2019, CES was all about 8K video and displays, because at that point, 4K displays were ubiquitous. If you bought a TV in 2019, chances are it was a 4K TV. There wasn't even a discussion about it. And 2020 really wasn't much different than 2019 because of the COVID outbreak. So, you know, a little bit of uncertainty there. However, demand for televisions has spiked. And we're seeing a very interesting thing happening. Television prices have dropped. Now television prices are starting to creep up a little bit, because there's such a demand for them, then the manufacturers can barely keep up with shipments. Give you an idea of some of the trends that are going on with projectors, an interesting part of the market. In 2019, there were 120,000 global 4K home projector sales. In 2020, that increased slightly to 127,000. 2021 is projected to be 164,000. That's quite an uptick. If we're looking at content in the upper right, the percentage of US Netflix subs that can get the premium plan, 4K plan, by the end of 2019, it was 25%. By the end of last year, 31%. So there's an increased interest in watching 4K at home. And globally, all the 4K streaming video on demand subscriptions that are capable of accessing it on a 4K TV, 209 million in 2019, and that number almost doubled in 2020. Well, no surprise, a lot of people were stuck at home and watching a lot more television than they planned on. They couldn't go to a movie theater because of the COVID outbreak. And again, TV sales were up last year. Sales of large screen TVs were up considerably last year. So I guess it shouldn't be a surprise at all that the number of people that are now watching 4K via streaming services has doubled in just a year. Now, when most people talk about 4K Ultra HD, they're talking about more pixels on the screen, but there really is more to the story. It is more than just additional pixels. For one thing, the screen sizes are getting bigger. We have new technologies for displays that have emerged along with UHD. We have high dynamic range, wider color gamuts. We have UHD projectors have finally come to market. HDMI and Displayport connections have gotten a lot faster. 8-bit color reproduction is no longer sufficient for Ultra HD because of high dynamic range and wide color gamuts. We need the additional bits to be able to show those pictures accurately. And an interesting trend, streaming content, Ultra HD content, is basically pushing optical disc into extinction. So let's start with some of the basics. One of the things that we talk about when we talked about display resolution, we wanted to have enough pixels on the screen so we wouldn't actually see the physical pixels. In the early days of displays, this is going back to the 1990s, we had something called the screen door effect, where you'd see a picture, but you'd see what appears to be a screen looking through a window screen at it. Well, that's actually the physical pixels. So to avoid seeing the pixels, you want to sit back a certain distance from the screen, at which point you don't have enough visual acuity to actually see the pixels. So if you look in this table for a 720p resolution display for a 55-inch diagonal screen size, the pixel pitch is about 1 millimeter. So if we go to 1080p, it drops to 0.6 millimeters. If we go to 4K, it drops to 0.3 millimeters. And if we go to 8K, it drops to 0.15. Well, what does that mean? Well, that means that you can sit closer to the screen intuitively. Keep in mind that high definition TV, which was actually developed in the late 70s and early 80s, was built so it was created so people could sit closer to a TV screen. So a 55-inch full HD TV is a recommended viewing distance of 3 times the screen height. So for a 55-inch TV, the screen height is 81 inches. The 27 inches is screen height, 3 times that is 81 inches, which is about a little less than 7 feet viewing distance. And that's a very common viewing distance in the home. What that means is at 7 feet or greater, you won't see the pixel structure. The picture will just appear to be seamless. So if we take that 55-inch TV and we now create a 4K pixel structure, so we've doubled it horizontally and vertically, we're cut the viewing distance in half. Now you can sit 3.5 feet away from the screen before you start to see the actual pixel structure in the screen. And with 8K, we can cut it in half again. So theoretically, with a 55-inch 8K TV, you could sit just under 2 feet away from it and you still wouldn't see the pixel structure. But that's not how it works. People don't move their chairs closer to the screen to watch TV. What they're doing is they're making the screens larger. So the real benefit is you don't sit closer to it and the screen gets larger. There's quite a difference moving from 720p or full HD to Ultra HD. But not quite as much of a difference moving from Ultra HD to 8K though. There was an interesting study done last year by Warner Brothers, a blind study where content was shown on 4K and 8K displays, and about half the people could see a difference, and about half the people could see no difference at all. And at the normal viewing distances in the home, you'll never see it. So we don't need to obsess about how close we can sit to the screen. We just make the screen larger, but we supercharge it by adding high resolution with high dynamic range and the wider color gamut that creates images that are more lifelike than anything we've seen before. Some definitions are useful. The Consumer Technology Association defines Ultra HD as a display with a resolution of 3,840 horizontal pixels and 2,160 vertical pixels. It has 4 times the resolution of a full HD display. And there's an additional blanking interval. It's not really blanking, but there's an additional amount of pixels that travel along with it for synchronization and other functions. So it's 4400 by 2250 is the actual full blanking interval. The reason that's important is that influences the speed of the display interface and also being able to move the signal around. The aspect ratio is 16 by 9 or 1.77 to 1. Cinema 4K, because we use the terms 4K and Ultra HD interchangeably, but Cinema 4K, not something you're likely to see on a consumer screen. You will see it on a professional screen, typically on a monitor that's used for grading, color correction, exposure correction of movie footage. All that does is adds additional pixels in the horizontal axis. So now we have 4096 pixels by 2160. The aspect ratio is now 1.89 to 1. It's more squarish. And accurately, to speak accurately, this is true 4K. So Ultra HD, technically speaking, really isn't 4K. We just use that term to describe it. Ultra HD is a more accurate description of it. And the Society of Motion Picture and Television Engineers classifies it as Ultra HD-1, UHD-1. But Cinema 4K is a true 4K resolution because it has at least 4,000 pixels in one direction. And then 8K, which is still a bit exotic for the average person, although they're broadcasting it on a 24-hour basis in Japan now, 16 times the resolution of 2K or full HD. So 33 million pixels in each frame of an 8K image as opposed to a little over 8 million pixels for Ultra HD. The aspect ratio remains the same as Ultra HD. It's 16 by 9. NHK calls it super high vision. There's no difference between, there's no variations of 8K. There's no Cinema 8K or Consumer 8K. It's just 8K. And SMPTE classifies this as Ultra HD 2. So those are the 3 to remember. There's Ultra HD, which is the TV that you buy and use at home, and that's the content that you stream to your TV and you watch off of an Ultra HD Blu-ray disc. And then there's 4K, which is Cinema 4K, and then 8K UHD 2. So, enhancements, what really makes Ultra HD different than Full HD, not just more pixels. The one that is the most obvious, you see it right away, is high dynamic range imaging. What that means is that we're able to capture more shades of light and more shades of color over a wider range. So we can see much brighter highlights, much deeper shadows, and much more saturated colors. But it requires 10-bit and 12-bit color rendering to make it happen. Now, the TVs and displays that you see today typically can do 10-bit processing. And if you're looking at content that's being streamed or coming off optical disc, it's also being encoded in a 10-bit range, not an 8-bit range. So what qualifies as high dynamic range? Well, a normal video camera, depending on the model, has anywhere from 8 to 11 stops of light sensitivity. An HDR camera will go far beyond that, to as many as 14 to 15 stops of light. So with standard dynamic range, a full white screen has a value of 100 to 200 candelas per square meter, or nits. That's pretty common. As a matter of fact, old tube TVs, full white, was about 100 nits. But with high dynamic range, we're starting to approach linear light. So peak whites, specular whites, you think of somebody welding and you see sparks, or a candle, or light reflecting off glass, or light reflecting off water, kind of a value of 1,000, 2,000, 4,000, or even 10,000 candelas per square meter. The gamma curve from black to white is closer to linear light, closer to 1 than the older 2.2 or 2.4 that we've used for picture tubes, older LCDs, and projectors. And the volume of colors that we can show is increased considerably. And the gamut that defines that is the International Telecommunications Union recommendation BT 2020, as opposed to the old BT 709 gamut. So here's a picture I took outside my house to give you an idea, a better idea of what I'm talking about. The deep shadows in the hedge are measuring around 20 nits. It's pretty dark. The sun is well in excess of 100,000 nits. The clouds near the sun, 40,000 nits. The skylight on the house, 2,000. Sides of the tree, 400. The bushes, 1,200. And the grass, 800 nits. So the clouds are measuring 2,000 times brighter than the deepest shadows. That's an intrascene dynamic range contrast of 11 stops of light, only 11 stops. Specular reflections, like light glinting off something, maybe a plane passes by or off a car window, could easily push that over 100,000 nits. But at the same time, the camera is capturing over 1 billion shades of color. So that's an enormous volume of color and luminance that's all being captured at the same time. Let's talk more about color spaces. On the chart, you'll see the yellow line. The yellow line represents the color space that we've used for a long time with LCD TVs and projectors. It's the ITU BT709 space. It's not that much different than the space that we used to show color on tube TVs. It's just a little bit wider. So it's got reasonably deep reds, very deep blues, and a little bit pushing up into green and yellow. But the new color space that we have with high dynamic ranges has a much larger area up in here in green and yellow. And that's the 2020 space. We've also pushed the red down a little bit further. So we add a red volume. The blue stays about the same, gets a little bit further saturation, but the green pushes way up. So the total number of color shades for 10-bit color is over 1 billion, whereas for 8-bit color, it's only 24 million. So 8-bit color cannot be used to display Ultra HD content with HDR. It's inadequate, just not up to the job. So the challenges of showing HDR are many. First of all, the content is mastered at different brightness levels. If you're watching something that's been encoded with Dolby Vision, that's their proprietary high dynamic range format, the target for mastering, when you're in a color mastering suite and preparing the master file, the digital intermediate file, is 4,000 candles per square meter, full white. That's really bright. Go look at an LED sign outside when it's showing mostly a white background, and that won't even be 4,000 candles per square meter, but it's pretty bright. Quantum dot equipped LCD displays can achieve 1,000 to 1,500 candles per square meter. OLED TVs that use a red, green, blue, and white matrix can achieve about 800 candles per square meter. Home theater projectors can achieve 3,000 lumens. That's 280 nits on a 100-inch screen. So a 280 nit display is pretty bright if you're looking at white at home. Not 1,000 nits or an 800 nits, it's still pretty bright. And the challenge that this creates is, how well, if you've mastered at 4,000 nits, how do I get it down to 1,000 or 800 nits so it looks right on that TV? So with Dolby Vision, it's done on the fly. It's basically done as it plays off the device or off the streaming service into your TV. Technicolor has a system where they can take standard dynamic range video and high dynamic range and mix it in the same stream so that a display that can only show standard dynamic range will only see the SDR content. High dynamic range display will see the HDR content. The basic format for doing high dynamic range is something called HDR10. All displays support HDR10. It's called static tone mapping. It's just a fixed set of values from 0 being black all the way to whatever white happens to be. But we have dynamic tone mapping, which is what Dolby does, and then there's something called HDR10+, so the highlights can be shifted per scene. And then we have a static gamma curve for both high dynamic range and standard dynamic range displays called hybrid long gamma, which was developed by the BBC. And HK had some input into it, but it's largely a BBC product. So any of these systems, primarily Dolby Vision, HDR10+, and hybrid log gamma, is liable to show up at the input to your display. And your display should support all of them. It should be able to recognize the metadata in there and know how to reproduce the content appropriately. So there is a standard for this. It's called 861.3 that the Consumer Technology Association came up with. There's a bunch of extensions to it. Most Ultra HD TV models and all 8K models will support high dynamic range. I would say at this point, just about any Ultra HD TV model will now support high dynamic range. Now, some projectors support it. Just make sure you check the specifications. So if you want to watch static metadata, it should support version 2.0A. If it's going to show Dolby Vision, Technicolor HDR10 Plus, it has to support version B, and if it's going to support hybrid log gamma, it should support version 2.0G. So if you buy a projector, you look in the specifications and they should tell you that which of these they support. And in most cases, they're going to support B and they're going to support A, B, and G. They should support all three of these. Displayport, which is primarily a computer interface, no manufacturer supports that interface on a TV. Some projectors support this format. It's still mostly a computer display connection, but Displayport also will pass version 2.0A, 2.0B, and 2.0G. So it is HDR compatible. The third leg of the enhancements to Ultra HD is the one I think it's the coolest: high frame rates. So we need displays that can handle 90, 100, and 120 frames per second refresh rates. Why? Well, we want to watch sports without blurring, and we want to do gaming. And it's very important for gaming that you have a display that can keep up with your laptop. SMPTE has standards for this, 2036.3 and 2048.3, that go all the way up to 120 hertz at both 4K and 8K resolutions. To give you an idea just how much data that is, if you want to be able to display 8K video at 120 hertz, with full RGB video, it's 192 gigabits a second uncompressed. That's an enormous volume of data, and it would have to go over a fiber optic cable. But it can be done. Let's talk about some of the display technologies now that we have for Ultra HD and 4K. So for HDR and wide color gamut, we can't use conventional designs for backlights and LCDs or self-emissive displays. We have to add some horsepower to it. We got to soup it up. So for direct view displays, quantum dots, which you may have heard of, high color luminous intensity with LCDs. This is a very common solution to do HDR on an LCD display. Organic light emitting diodes. They can't get as bright as an LCD with quantum dots, but they still do a pretty good job on their own. They can get up to about 800 nits, small area white. And something that's coming down the pike that you want to keep your eye on, it's not here yet, but we're starting to see some products being released, mini and micro LEDs, mostly used as backlights to increase the amount of light coming through the screen to do HDR. But we're starting to see some actual TVs. They're very high-end, very expensive, but high-end TVs made out of micro LED arrays. And in theory, these particular TVs can get as bright as 1,600 to 2,000 candelas per square meter, which I assure you is more than adequate for watching at home. In fact, it might be too painful to watch. For front projection, digital light processing, which is the technology that BenQ uses, and DLP is used in cinemas to show high dynamic range, wide color gamut films and movies. So it works quite well for that. Liquid crystalline silicon, LCOS, that is basically the technology that's used in Sony projectors in movie theaters. And then lasers. And these are not the same lasers that you would associate with a laser light show or anything. These are just basically laser light sources. So we have very intense red, green, and blue, but we require diffusion. We can't use specular light because you'd see all kinds of weird artifacts on the screen. So we're just taking all that horsepower from a laser, diffusing it, and then combining red, green, and blue to get full white, and typically with a light modulator like a digital light processing or liquid crystalline silicon. So any of these will do high dynamic range, and they'll do a good job with it. Quantum dots are tiny little particles. You can't see them. They're extremely small. And basically, they're just little dots made out of metals that when you bombard them with high intensity light, typically blue light, they then emit green and red light and also blue light, which is a quantum effect. You're taking energy of one kind, you're converting it to energy of another kind, which is quantum energy process. So when you hammer these dots with blue light, you get a very intense green and you get a very intense red. The size of the dot determines the wavelength of the color, and these can be added as a layer, either as film or on glass or some other way, to a backlight for a TV. And the blue LEDs serve two functions. Number one, they provide the energy to fire the red and green quantum dots, and they also provide blue light to round out the picture for RGB color imaging. The best color typically comes from a compound known as cadmium selenide, and it's doped with zinc. The problem is cadmium is considered to be a toxic heavy metal by the European Union and California and other places, so we don't really want to use a lot of it. A more green technology to do this would be indium phosphide. So a lot of TVs use indium phosphide, some TVs use indium phosphide and cadmium selenide. OLEDs can do HDR. Technology is mature now. You can buy OLED TVs. They're sold primarily for consumer televisions. There are some professional models as large as 88 inches. They all have 4K Ultra HD resolution. You will not see them at any lower resolution, and there are some 8K models available. Pixel matrix is red, green, blue, white to boost the brightness, but also to maintain the low black levels. And they do sell at a price premium to LCD TVs. They're not as bright, but they do a very nice job with high dynamic range. Because remember, as I said earlier, you need to be able to do 11, 12, 13 stops of light. Well, an OLED TV coming out of black can almost do 20 stops of light. Inorganic LEDs, iLEDs, as I call them, are interesting. LCD TV manufacturers are using more of these now in full arrays, the goal being to try to match every color pixel with a little LED emitter, 1-to-1, which uses quite a bit of power, but gives you a pretty spectacular image to achieve HDR and better luminance uniformity. So these backlight designs can have hundreds of zones of mini LEDs, which actually measure about 100 micrometers and up in size, between 100 and 200 micrometers. Mini LEDs can also be used as direct view displays. You can look at them directly. There's an 8K video wall in the picture, and they make what's called a fine pitch video wall. Right now, you can get them with pixel pitches down to 0.8 millimeters, which is good for 4K or 8K in a large screen size. And as I mentioned earlier, we're starting to see actual televisions for the home coming out that are made out of micro, although they're more accurately classified as mini LEDs. But micro LEDs, that's if you've got a few $100,000 to spend on a television. Micro LED displays, several manufacturers have shown these at CES, ISE Infocom, the NAB show, Digital Sign Expo. They have very wide viewing angles, high dynamic range, wide color gamut, and they can refresh as fast as 3,000 hertz. So to do 120 hertz high frame rate, it's a piece of cake for them. They're barely loafing along at that speed. First TVs were introduced in the fall of this year with this technology. And most analysts, and I would agree with them, predicting this will become the dominant display technology by the end of this decade, that we're going to see micro LEDs used everywhere, from your phone to your laptop to your television to stadium signs to outdoor advertising billboards and screens in boardrooms and classrooms. What about projection? All three imaging devices actually got to 4K resolution quite a while ago, some of them almost 20 years ago. DLP projectors, used for high brightness projectors in large venues, also for home theater. LCOS already deployed for digital cinema and some large venue projection, and high temperature polysilicon. Prototype 3 LCD panels for 4K have been manufactured and shown, but they really haven't been deployed yet. So right now, if you're looking for 4K in a projector, you're looking at either DLP or LCOS. The 4K projector focus has been primarily on the home theater market and high brightness large venue. So really, really large venues like indoor arenas, movie theaters, exhibition halls, and experiences, amusement parks, places like that, simulation. That's what they look like. So across the top, a 4K 3 LCD, high temperature poly. In the middle of 4K DLP, there's multiple 4K chips. There's the full-size cinema chips. There are smaller chips. I'll explain how those work in a minute. And up in the upper right, the SXRD 4K LCOS. So there's a Barco 4K cinema projector that can use lasers. And on the right, a home theater projector you can buy right now to do 4K. So the light sources at the moment for 4K and Ultra HD are high-intensity short arc lamps, xenon mercury, and ultra-high pressure lamps. However, the projector industry is moving away rapidly from short arc lamps as fast as it's feasible, mostly because these lamps contain halides of metal, mercury, and other salts in them, which creates an environmental ROHS issue if you're trying to dispose of them. You don't have that problem if you're using lasers or you're using laser phosphor hybrids or lasers with LEDs. The laser phosphor hybrid is a very popular way to create light for a projector. They're now up to 50,000 lumens, which is a pretty bright image. And RGB lasers with diffusers, I mentioned those earlier, those can do up to 50,000 lumens as well. And LEDs, just red, green, blue LEDs in chips can get up to 2,000 lumens. And any of these would be instant on, instant off projectors. They're just like turning on and off a light switch. Now, this is something that I know people find confusing, but it is a very effective way to get to 4K or Ultra HD resolution, but you don't need to have a 4K or Ultra HD imaging chip to do it. So the native resolution chipsets will have 3840 by 2160 or 4096 by 2160, but they're quite expensive and they're used for digital cinema. But DLP chips, which are actually called digital micromirror devices, they have little tiny mirrors that tilt back and forth at a pretty narrow angle, and they can move at incredibly fast speeds from on to off. So what they can do is by changing the angle, they can map all the quadrants of an image in rapid succession in full color. So that enables the projector manufacturer to use a smaller, lower cost DMD to build to get to 4K resolution. Fortunately, nature has blessed us with eyes that can't keep up at that refresh rate. So what we see is a flicker-free 4K or Ultra HD image. We don't see all these intermediate steps being mapped. So the upper left, the upper right, lower left, lower right, we just see a full image, and we see it at 60 times a second, or we'll see it at 100 times a second or 120 times a second. So there is no flicker visible, and the result is now an affordable 4K projector, because otherwise the home theater projectors using the full chips would be a lot larger and cost you tens of thousands of dollars. Now we have projectors that are a heck of a lot less expensive. And that's one of the chips on the right. The TI DLP 471 is commonly used. I believe this is a 0.47 inch chip. And the actual resolution is lower than 3840 by 2160. But because of this cool trick of physics, it will map each image fast enough to see them as full frame images at whatever frame rate you choose to watch without flicker. All right, well, how about UHD on computers and mobile devices? There are a number of 4K laptops out there. Here's one that I found recently, the Dell Xps 15. These are all, to my knowledge, tracking this market. They're all using at least the Intel i7 CPU because they're primarily gaming machines. And they have to have an equally fast video card. So this is a GeForce GTX. Now, it has 4 gigs of RAM in it, but typically these things will come loaded with 8 or more gigs of RAM because of the refresh required. It is a 32 gigabyte solid state drive, and it's got 2 racks of 16 gig memory chips. I'm sorry, it's 32 gig DDR, 2 by 16, so it's 32 gigs of memory chips. I got mixed up on the specs here, my apologies, which is a lot. Typical laptop doesn't come with 32 gigs of memory and 1 terabyte drive, and they're all solid state drives now. So it is a 15-inch, almost 16-inch Ultra HD display, 3840 by 2400, not 2160, 500 nits. That's an extremely bright display for a laptop, extremely bright. It has 2 Thunderbolt ports and USB-C 3.1 for an external monitor if you want to connect it in alternate mode. So 2350, that's one heck of a fast computer. And there are other models, of course, and 4K cameras are everywhere. I mean, GoPro, Zcam, Blackmagic Design, any number of companies, Sony, Canon, JVC, the large manufacturers, all build them. So you have cinema quality cameras, you have consumer quality cameras, you have prosumer cameras. Prices range anywhere from $200 to $5,000. They can use 1/3 inch, 2/3, and micro 4/3 sensors. The video is usually shot as 2160p 30 for consumer cameras. For professional cameras, they can go to 60 hertz or even faster. And we even have some cameras, because of the odd pixel count of their sensors, that can actually capture 5K video. And we also have had some prototype cameras shown that can do 8K and 10K video. But you can basically go online right now or walk into a store if they're around, and you can pick up a decent 4K camera for $400 or $500. It'll do a very good job. Or you may find you have one on your phone, or you can get a DSLR that'll do it. And believe it or not, there are actually smartphones that will show HDR and record 4K. Sony's Xperia XZ2 model recorded video at 4K resolution. The displays were not 4K, but they're better than full HD. They're better than 300 dots per inch or pixels per inch resolution. The problem is it creates enormous files on your phone, so you have to have quite a bit of storage. And then how do you get those files off the phone? Great, you shot 4K video, but how do you get it off the phone to somewhere where you can use it? And now we're starting to see, believe it or not, 8K smartphones. I think Samsung introduced a couple of their high-end phones now they claim will actually shoot 8K video. I'd want to investigate that claim a little more carefully. How about connecting all this stuff? Well, the minimum interface that you need to show any kind of 4K or Ultra HD video with HDR is HDMI 2.0. This is a maximum data rate of 18 gigabits a second. It cannot go any faster. It can't pass any signal that requires a faster data rate. So that is fast enough to do 10-bit video at 420 color resolution. That's lower color resolution. 4K 60 frame or 8-bit RGB at 60 frames. But it can't do 10-bit RGB 60p 4K, which is not unusual to get that off a computer video card. So you have to cut the color resolution to 422 or 420, 420 being a consumer format, 422 being a professional format, and 444 full resolution video on all color channels being a computer format. You have to cut the color resolution if you want to maintain the frame rate and also 10-bit encoding. HDMI 2.0 is barely fast enough for 8K 30p 8-bit, which is almost useless at that point. If you're going to look at 8K and you can only do it at 30 frames a second and you can only use 8-bit color at low color resolution, why bother? Believe it or not, the first 8K TVs that came to market, that's all they could do. I felt bad for the people that bought them because they had a heck of a time trying to get a signal through them. So your streaming boxes, streaming sticks, Ultra HD Blu-ray players, anything you use to get Ultra HD and 4K content needs to have an HDMI 2.0 output at the minimum. Now we have a faster version coming out, HDMI 2.1. The data rate on this went up quite a bit. It went up to 48 gigabits a second. And I put an asterisk there because at the moment, it's very difficult to run that fast a data rate over copper, over any length of copper. So it might require an optical fiber connection to run at 48 gigabits a second. But this now gets you into a bit of a larger playing field, a more comfortable ballpark to do 16-bit 4K, Ultra HD, 24 frames, 30 frames, 60 frames. So it really is perfect for gaming. And it's also fast enough to do 8K 60p 422, which is almost 43 gigabits a second. But again, it's a challenge to use copper at that speed. That's really more of a professional format. And indeed, if you go to one of the professional shows like NAB or Infocom or IBC in Europe, you will see cameras that can actually output this signal. But if they're going to do it, they're going to do it over the serial digital interface connection, or they're going to do it over a really, really fast display connection. HDMI 2.1 interfaces are just starting to appear on consumer TVs. They are backward compatible with earlier versions. So if you have a slower signal, that won't be a problem. But if you have a high-speed signal that is faster than 18 gigabits a second, you're never going to get it through an HDMI 2.0 connection. So that's the main reason I'm pointing this out. So 2.1 is just starting to roll out, something you want to keep your eye on for. But in the meantime, 2.0 should handle a lot of the viewing that you want to do. I mentioned Displayport earlier. The maximum data rate for Displayport is 21.6 gigabits a second. And it's been that way for quite a while. Displayport 1.2 was actually announced in 2009. And if you look at a computer that supports this, it's 9 times out of 10, it's going to be version 1.2. Version 1.3 came out in 2014, but I haven't seen a lot of computers supporting it. And in the world of consumer electronics, the TV guys say Displayport is a computer interface. That's for the computers. The computer guys say HDMI is a TV interface, although you are starting to see more computers that support HDMI. The beauty of Displayport is you can convert it easily to HDMI because Displayport carries a small amount of power on one of the pins. You can build a converter right into it, and you can plug a cable in and you can get HDMI out of a Displayport connection. Not so easy to do it the other way. It's kind of complicated. It's fast enough to do 4K 60 10-bit color. That's my benchmark. My personal benchmark is that I'd want to be able to show 4K or Ultra HD content at 60 frames a second using 10-bit RGB color, like off a computer. If you can do that, that's great. That to me is fast enough. But it can't handle 4K at 60p, 12-bit or 16-bit. That requires a faster interface. It can pass a 8K30 10-bit 420, so a little bit better than HDMI 2.0 can. Now I mentioned 1.3 and 1.4. These have been around for a few years. The manufacturers have been slow to adopt them. There are some computers that will support these interfaces. The data rate's now up to 32.4. Again, that gives you a lot more room to play with. So it'll do 4K 60p 12-bit and 16-bit color. It can also do 8K 30 10-bit 422 color. So you're going to find this on more expensive high-end gaming and graphics cards and on premium laptops with 4K displays. Basic laptops, probably not likely to see it. And I should mention that both HDMI 2.1, which is digital, it's basically the same sort of thing as Displayport, uses the same signaling method. Both HDMI 2.1 and Displayport, all 1.3 and 1.4, can run something called alternate mode. And alternate mode means that you have a USB port on your computer, USB Type-C port. That's the little one that has 24 pins on it. That can actually double as a display connection. So if you plug a computer monitor into that port, your computer will say, hey, he plugged in a display. And all of a sudden, it's now working as a display connection. So if you have both HDMI and USB Type-C on there, you can have two displays running at the same time. So this is a trend that we're seeing in the industry. It's to reduce the number of connections on laptops and mobile devices to, say, one connection. And it's a so-called smart interface. It knows what you connected to it, and it configures itself accordingly. And by the way, just because you're using it as USB-C as a display doesn't mean you can't also do data interchange through that connection and also power for charging the mobile device. So it can do up to 3 things at the same time. So this chart kind of explains where everything is. At the very top there, you'll see HDMI 1.4, which is a standard that's been around for, since the mid-2000s. 1.4 came out with 3D, so let's say 2008, 2009. That uses a signal format called TMDS. I'm not going to get into it, but has a maximum data rate of 10.2. Can you support HDR with it? Nope. You can't do display stream compression. You can actually compress display signals, which is a cool thing. Nope, can't do that. Doesn't support Type-C. HDMI 2.0 has a maximum data rate of 18, so it does support HDR, but not DSC. HDMI 2.1 data rate is 48. It'll do HDR, DSC, and Type-C. And Displayport 1.2, 1.3, and 1.4. So 1.3 and 1.4 will support DSC and Type-C, but 1.3 doesn't support HDR, 1.4 does. And it's a little confusing, but the main thing is that you have to pick the display to match the application and find out what your device outputs and what the display will accept. So generally, the later versions of these are going to be the better versions to have. So 2.1 is not widely available yet as far as HDMI, but we're starting to see more of it on televisions. 2.0 should be pretty much available on anything. Anything that's claims to support 4K should have at least 2.0 on it. And for Displayport 1.2, 1.3, or 1.4, and then you have variations within those. I want to mention copy protection because we've been living with this for years. It started in 2001, version 1. Versions 1.1 through 1.3 were evolved in 2003 through 2006 for the HDMI connector. Version 1.4 came out along with version 1.4 of HDMI for 3D. And then version 2.0, which was introduced in 2008, can run on other interfaces. It's interface independent. So the later version of that 2.2 can work over anything. It can work over USB. So if you have a streaming stick that you have plugged into your projector or TV, and it's through a USB port, yep, copy protection can actually ride on that. Version 2.2 is developed specifically to be used with Ultra HD and 4K content, but supposedly it was hacked in 2015. As I'm fond of saying, even a suit of armor is no defense against a can opener. And then, of course, aftermarket strippers came into the market, that will remove copy protection. Of course, it's illegal to sell those things in the United States because that defeats the purpose of copy protection. So the latest version of HDCP is 2.3. This was introduced in February of 2018. Has a faster locality check and a more secure key exchange. All that means is that when you plug in a device with an HDMI or Displayport connection with HDCP, in about 20 milliseconds, it checks to see if it's a safe connection, if it's a copy protected connection and it has a valid key. And if it doesn't, then it just shuts it down. You don't see static or anything on the screen, you just see nothing. You just never see a picture. Whereas with the older versions 1 through 1.3, you would see kind of this weird red, green, blue hash on the screen like static. Now you just don't see anything. So versions 2.2 and 2.3 are not backward compatible with the older versions. The source to sink connection, when you plug it in, needs a response from the sink in less than 20 milliseconds or less. And 2.3 is 7 milliseconds or less. That's about as fast as you plugging it in. Literally the second you plug it in, it's already polling to say, do we have a copy protected connection here? If we don't see it, then the connection is shut down. You won't see the content. It uses very robust AES encryption, 3072-bit keys. That would be awfully hard to crack. What you'll see with some AV gear, especially signal switching equipment, they'll mix an older version of HDMI and a newer version of copy protections for 4K. So your older version might be 1.4, but your copy protection might be 2.2 or 2.3. So yes, you can run 4K through HDMI 1.4, but it's going to be at a lower frame rate and it's going to be at a lower color bit depth because otherwise you run into that speed issue. If you go above 10.2 gigabits a second, then it's not going to work. And those guys that went out and spent tens of thousands of dollars on those early Ultra HD displays, those things are basically bricks now because they will not support HDCP 2.2. So let's talk about projection versus television screens. Because it seems like everybody is running around buying large TV screens. So is there still a place for projection? Well, 55 inches is now considered a small TV screen. That's the median size. 65 inches up is a growth area. And we're now starting to see 8K TV models in this range. And of course, we have models ranging from 70 and 75 inches all the way up to 98 inches. Of course, those 98-inch ones are really, really expensive. So right now, practically speaking, the dividing line is around 85 or 86 inches. TV prices climb dramatically above the screen size. If you've gone to Costco or BJ's or Best Buy, or if there's still any Fry stores that are still open, or Target or all, you'll see this. Up to about 85, 86 inches, you can get a TV under $2,000. But once you get above that, they go up into the stratosphere. And also TVs as large do require specialized installation because they're heavy. They're big. And with the 8K models, we're starting to see a problem with power consumption. So is there really any benefit to going to 8K? It's a fair question to ask. A UHD 85-inch TV with high dynamic range that's using a really, really dense mini LED backlight to accomplish HDR can consume 450 watts. But the 8K version, not surprisingly, is double that, 900 watts. That's a lot of power consumption for a TV. We haven't seen that since we had plasma TVs years ago. So the fact remains that if you really want to do a cost-effective way for getting images larger than 85 or 86 inches, you're going to have to go with projection. And to give you an idea here, I did some online pricing. So I picked the average price of 5 different tier 1, this would be primary manufacturers, primary brands, 85, 86-inch Ultra HD TVs with smart operating systems, ties in Android WebOS. The average price was $1,800. The BenQ TK850 4K projector is $1,500, and the HT3550 is $1,500. This is based on Best Buy advertised prices from last month. So you're in the ballpark as far as price. On a typical TV, let's do an apples-to-apples comparison. Luminance levels for TV calibrated for ISF-day, like my LG 55-inch OLED, bright luminance levels range from 75 to 150 nits. That's with diffuse white. Well, full diffuse white on the 850 is 3,000 lumens. That would be equivalent to a 280 nit on a 100-inch screen. And the HT3550 full diffuse white is 2,000 lumens. That'd be equivalent to 185 nits on a 100-inch screen. So we're in the ballpark. We're actually above the ballpark. So we're not giving up anything in terms of brightness for average viewing. Now, the other thing about televisions are direct view displays. They hold up pretty well under ambient light, but they're unaffected by contrast flattening due to ambient light spill on the screen. So if light is spilling on it, it doesn't really flatten the contrast unless you have a lot of outside light or inside light directly on the screen. But most TV models have high gloss screens because it improves contrast, and they reflect bright objects and they reflect light sources in the viewing space. So that there is that problem to deal with. And the screen size is fixed, so you have to match it carefully to the room. Projection screens don't reflect images of bright light sources that you don't want to see. They reflect light from the projector. So if you have a lamp in the room, it just flattens the contrast, but you don't see the lamp on the screen. It is throwing a little bit of light on the screen, but you don't actually see the image of the lamp. Image sizes can be customized from 40 inches to 200 inches. There's no need for gain screens. These things are bright enough now that a normal matte diffusion screen, a 1.0 gain, works just fine. So the real challenge for projection is to get that high contrast ratio. And we really want to be in a target of 80 to 100 to 1 over room ambient for immersive viewing. For everyday viewing, it'd be 20 to 1 to 50 to 1. If you're going to watch the news or other programming, and we're not that worried about it. So I want to show you the importance of the contrast ratio with a few slides here. Projectors work better with managed ambient light levels. Everybody knows that. Control the ambient light, you see a better image on the screen. Our targets are contrast ratios between screen brightness and room ambient. And here's some useful rules of thumb. You may not know this, but to read a book, you only need about 7 to 1 to 10 to 1. For viewing still images, maps, or documents, 15 to 1 to 30 to 1 will do the job. For casual TV viewing, 30 to 50 to 1. For immersive viewing, 50 to 81 or better. And it's hard to get a lot higher than 50 or 60 to 1, unless you're in a room with black walls and people are wearing black clothing. It's really hard to dampen that ambient light. These are not hard and fast rules, but they're really desired targets that you want to get to. So here's my home theater. I have full ambient room lighting. Those are LED lights. And the contrast ratio between what I see on the screen to the highest room ambient is only 7 to 1. I mean, I can see things on the screen, but it's mostly things with light backgrounds and dark text. If I shut off the front lights and leave the back ones on, I've now improved the contrast in the room to 34 to 1 with 50% of the lights on. And we've actually watched programming this way. But for best results, we want to drop all the lights in the room. And now I'm at 51 to 1. That's a little below where I want to be with immersive, but trust me, it's pretty immersive at this point. And I am seeing a reflection off one of the projectors, the ceiling, some other things, but I just live with that. Let's also take a look at content. Okay, this is where most of the 4K content is coming from now, is streaming from the cloud. Low-cost Ultra HD sidecar media players and sticks are widely available. Everybody knows Roku. We also have streaming sticks. I just read today that Walmart is thinking of coming out with a streaming stick or a little box that'll be lower priced than Roku. Apparently, they're going to be starting their own streaming service. All of these players support H.264 and H.265. These are two different codec standards, MPEG-4 and MPEG-5. Again, Roku is the best known of all, but you have to be careful when you buy one of these. Some of the earlier models don't support any HDMI interfaces faster than 1.4, which will only do 24 or 30 frame. You want to have at least HDMI 2 on it. And these boxes will all support the three different HDR standards I mentioned before, 2.0A, 2.0B, 2.0 D and G. And as we all know, you can get HDR programming from Amazon Prime, Netflix, HBO Max, Hulu. We are watching The Magnificent Mrs. Maisel right now, and that's in HDR, and it looks spectacular. You'd need about a sustained 30 to 50 megabits a second broadband connection for 4K. Netflix claims you can be as low as 15. That's cutting it too close, in my opinion. You really want to be up above 25. And that shouldn't be too hard to do nowadays, because most broadband providers now will give you that as a mid-tier speed. Now, what about Blu-ray? This was a big deal back in the late 2000s when there were two competing standards, HD DVD and Blu-ray, and we all know Blu-ray won, and then it evolved into Ultra HD Blu-ray. But funny thing about that, people aren't really watching discs so much anymore. That there was some uptick in disc watching during the pandemic. Libraries mentioned that a lot of the discs they usually kept in stock were gone. People were checking them out because everybody was stuck at home. They're frantic to find anything they can watch, keep the kids busy. So most manufacturers have actually stopped making the Blu-ray players. To my knowledge, at the moment, the only ones that you can still buy out there come from LG, Sony, and Panasonic. These support high dynamic range, wide color gamut. Prices as low as $180. Sometimes you can get them even lower than that on sale. This is a high-end one, this particular Panasonic model. The thing you need to also check into if you want to go this way is that not all high dynamic range formats are supported in all the players. So you may find that one supports Dolby Vision, another one does not. That is actually kind of working itself out. I will tell you that I put Dunkirk on an Ultra HD player. I have an LG here, into a 4K TV with high dynamic range. It just blew me out of my chair. I mean, it still is the best looking picture out there. But a lot of us have decided we don't want to own discs. We don't have big libraries of discs. We don't want to bother renting discs. And it's just easier to stream it because the content's available from so many different streaming sources. As far as digital TV goes, in the United States, ATSC3 is the next generation of digital TV broadcasting. There are probably 40 or 50 stations now doing test broadcasts all across the country of ATSC3. It's really more of an IP-centric system. It's kind of like streaming, but it happens over the air. It uses the HEVC 265 codec, which is good for doing 4K and possibly even 8K. And it's very efficient at compressing signals. So a TV station can transmit standard definition, high definition, and 4K video of a program all in the same channel. Now, that's not all that likely to happen because what most broadcasters are doing is carrying multiple different programs in a channel, but technically it's capable of doing it. And this means that with a device in your house, let's say like an ATSC receiver built into a Wi-Fi access point or modem, you can actually stream the content in your house to smart TVs, laptops, tablets, whatever you want to watch it on, from your home Wi-Fi network. Now, 4K digital downloads and streaming surpassed optical disc in 2019 for good. I don't even think it optical disc caught back up in 2020. The reason that streaming passed optical disc many years ago, but 4K, when it first came out, nobody was doing it. The only way to get it was on optical disc. So optical disc took the lead again, but in 2019, streaming passed it, and it's not going to turn back. As more homes get fast broadband connections, it's easier to stream in 4K. And we're continually improving video compression codecs to make it possible to stream Ultra HD content with HDR reliably to the home. And as more and more content becomes available on everything from HBO Max and Disney Plus to this new streaming service. I'm hearing Amazon wants to buy MGM and they'll start a streaming service. That's depressing sales of UHD Blu-ray players and discs. Fewer people want the discs. Right now, the three most popular outlets for streaming remain Amazon Prime, Netflix, Hulu, and then secondarily YouTube, which is building up a pretty good 4K package. And if you want to, you can go out on the internet and watch NASA. I don't know if maybe you've ever looked at it, but there's some awesome video that's coming live from the space station in 4K on a daily basis. But overall, we are definitely heading towards a disc-less world with everything in the cloud. That's where it's all going. So optical discs, the players and all that, they'll be in the same pile as your VHS players and Laserdisc players and 8mm movie cameras and all those wonderful things. It's only a matter of time. So I don't know, asking our organizers if we want to take any questions at this time, or if not, we can call it a day. So let me know what you would like to do.
We have one question. Can you see it in your chat box?
Okay. Yeah, I will take a look at it.
Yep.
Okay. There are currently no commercial projectors that support variable refresh rate. Is it even possible to have VRR on their current projector tech? Texas Instruments DLP. Right. Variable refresh rate is intrinsic to HDMI 2.1. I mentioned earlier that we can do tricks with display interfacing, so we can actually compress the signal. Well, we can also change the refresh rate through the interface. I would say at the moment, I'm not aware of any commercial projectors that support it, only because it hasn't been that long that the HDMI 2.1 chipsets for both transmit and receive have actually been rolling out to market. So that's a relatively new feature in HDMI. And you have to expect that there's going to be some lag time between the availability of the chipsets, which I'm sure has been also affected by this worldwide shortage of chipsets. I don't see why that would be a problem to implement in any display. And if you can do it in a direct view display, it should be easy to do it on a projector. It's just going to require additional onboard processing. It's also going to require the projector to support a wider range of frame rates. Keep in mind too that a lot of the CTA standards, and this is useful to know, are based on a standard fixed clock rate. So they did that to economize on the cost of building TVs. So if your base clock rate is 72.5, I think it is, or 74.5, that would be 720p 60, 148.5 megahertz would be 1080p. 297 is 2160p 30, and 594 is 2160p 60. So in some cases, no, the displays would not be able to support it if it's anything other than the base clock rates based on the CTA standard. But it can be done. It just requires additional processing within the display, whatever the display is, to be able to handle different frame rates. DLPs should be able to do that because the light modulators in there can run at extremely high speeds, so it would not be a challenge. But I think it's something that's going to take a little while to come to market. And I think that's the only question. Okay, well, if that is it for the questions, I'd like to thank everybody for joining today. And I hope you learned a little bit more about 4K. Sometimes the marketing and promotion stuff gets a little bit out ahead of what the actual facts are, but I hope I've given you enough of that to understand the differences in terminology and how the whole signal chain works, where you get your content from, the challenges with interfacing, where the current display technologies stand, and where content is coming from. So once again, thank you very much for tuning in. Thanks to BenQ for sponsoring this seminar, and have a good afternoon.